Today we're going to take a look at continuing to work with linear equations, but this time we're going to see more than one equation that we're working with simultaneously. What we're going to do is we are going to use systems of linear equations to solve problems. And to do that, first we need to make sure we know how to do these systems of equations. So we're going to do a quick review of systems. First way we have to solve systems of equations, two equations working together simultaneously, is we can solve them graphically. So if I wanted to solve y equals negative 2/3 x plus 1 and y equals 4/3 x plus 7, I could do that on a graph. So let's graph it. I got this graph here. We're going to remember that slope-intercept form from a couple days ago, y equals mx plus b. We're going to start at b, the starting point. So b, the y-intercept for this first line, is 1. So put a dot at 1 on the y-axis. And then the slope m is rise negative 2, run 3. So I'm going to rise down 2 over 3 and put a dot. And then we should be able to connect those dots with a straight line. So now we're ready to connect the dots, and I'm just going to draw a line here through those points. It's not going to be a perfect line, but it'll do the job. And then we can graph the other line just the same way. We know that b, the y-intercept here, is 7. 1, 2, 3, 4, 5, 6, 7 up here. And then slope is going to be to rise 4 and run 3. We really can't rise 4, so I'm going to work backwards. I'm going to rise negative 4 and run negative 3, backwards and backwards. So down 4, backwards 3. You can go again, 1, 2, 3, 4, down 4, backwards 3. And when I connect this line, we get these guys. Now what we see here is the blue line represents all the solutions to the first equation. The green line represents all the solutions to the second equation. We want the solution that works on both, and that's going to be where both of them overlap. And if we count that, that's at negative 3, positive 3. So that's going to be our solution to this equation. Negative 3, positive 3 is the xy value that works for both equations. So that's how we can solve graphically. The problem with graphically, though, is it only works when the solutions are nice, pretty numbers, and our graphs are perfectly accurate. If we get off by a little bit on our graph, it can make a drastically different solution. So graphically is probably the worst way to solve an equation. So we've got two other ways that are better. One that's probably used the most is called substitution. Substitution is where we find a lone variable to substitute in the other equation. So let's do a couple examples of substitution where we do that. Let's say we have y equals 3x minus 1 and y equals negative x plus 7. Now what we notice is, wrong color. What we notice is we've got this y equals stuff. That means in the other equation, I can replace the y with the stuff. So it's y, which is going to be replaced with 3x minus 1, equals negative x plus 7. Notice I've replaced the y with the stuff it equals. Then I can just solve this equation. The parentheses really aren't needed because there's nothing to distribute. So I'm going to add x to both sides. That gives us 4x minus 1 equals 7. Add 1 to both sides. 4x equals 8. Divide by 4. And we now know that x equals 2. Still need to find y. We can do that by going back to that y equals equation that we substituted to begin with. Y equals 3x, which is 2, minus 1. Well, 3 times 2 is 6 minus 1. Y must equal 5. So for our solution, x comma y, x is 2, y is 5. This is where the two lines are going to intersect. No graphing required. Let's take a look at one more substitution problem that's a little more involved. So let's try this problem. Let's try x minus 2y equals 5 and 3x equals 7y plus 8. This time we don't have the x or y equals equation all by itself, but we can get there really quickly. You'll notice x doesn't have a coefficient on it. We can get him alone very easily if we simply add 2y to both sides of the equation. When we do, we'll end up with x equals 5 plus 2y. So if x is equal to this 5 plus 2y, we can plug that in for x in the other equation. The other equation was 3x. Now it's 3 times the stuff. 3 times 5 plus 2y equals 7y plus 8. Start solving. Start by distributing the 3. 15 plus 6y equals 7y plus 8. Get the variable on one side by subtracting the 6y from both. 15 equals y plus 8. Subtract 8 from both sides. 15 minus 8 is 7 equals y. Now we just have to figure out what x is, and we have this equation that tells us what x equals. X equals 5 plus 2y. X equals 5 plus 2y. Y we just found out was 7. So x equals 5 plus 14, or x equals 19. So these two lines are going to intersect at the point x comma y, 19 comma 7. So that's kind of our review of the substitution method. You need to find a lone variable, get it alone, so that we can substitute it into the other equation to get something we can solve. And this is what we will use most of the time. However, on occasion, getting that lone variable gives us a very ugly fraction that we don't want to deal with. So we have a third method for solving to help us around that method. This third method of solving is called elimination. Some people call it addition. You might have heard that also. And the way elimination works is we get opposites in front of one variable and add. So what I mean by that, a couple examples here. If I've got 2x minus y equals 7 and 2x plus y equals 13. When I say we want to get opposites in front of the variable, you notice that negative y and positive y are opposites. If we add them together, we get 0. That's what an opposite is. So because they're opposites, we can go ahead and just add these equations together. 2x plus 2x is 4x. The y subtract to 0 equals 7 and 13 is 20. This will give us an equation that's very easy to solve. Quickly dividing by 4 tells us that x is equal to 5. To find our y value, we go back to either of the original equations. There's no real better place to go, so I'll just pick the second. Both equations will give us the same answer. 2x, 2 times 5, plus y equals 13. Well, 2 times 5 is 10, plus y equals 13. So if I subtract 10 from both sides, we get y equals 3. And so the solution where these two lines intersect, x comma y, is 5 comma 3. Now this one was nice because it started out with those opposites we wanted. We had a negative y and a positive y. Quite often we don't start with the opposites we want, though. So we'll see a problem like 3x minus 2y equals 21. And 5x plus 4y equals 13. And we're going to have to do some work to get the opposites that we want in front of either x or y. And we can pick on either variable. It doesn't matter. So what I do is I look at the numbers and find the least common multiple and decide which least common multiple would be easiest to work with. Like in front of x, we've got 3 and 5. The least common multiple there is 15. That's kind of big. I don't know if I want to work with 15. Let's check the other side. Let's check negative 2 and 4. The least common multiple there is 4. If we can get one of them to have 4y and one of them to have negative 4y, those would subtract out to 0. We already have positive 4y in the second equation, so we're going to multiply the first equation by 2 on both sides. When we multiply by 2, that's going to give us negative 4y in the middle. So distributing through, we get 6x minus 4y equals 42. Now we have opposites. We've got 4y. We've got negative 4y. We're ready to add these equations together. 5x plus 6x is 11x. The 4y's go to 0. 13 plus 42 is 55. We can divide both sides by 11 real quick. And x equals 5. To find y, we go back to either of the original equations. It doesn't really matter which. I'm just going to pick the second one because, well, why not? So it's 5x. We just found out x was 5. Plus 4y equals 13. Well, 5 times 5 is 25. Plus 4y equals 13. Subtracting 25 from both sides, we get 4y equals negative 12. Divide by 4, and y is equal to negative 3. So x comma y, 5 comma negative 3, is the point at which these two lines are going to intersect. Now this equation, we had to multiply one of them by 2 in order to find those opposites we wanted. Sometimes, though, we have to multiply both equations by something in order to get the opposites we want. So one more problem by way of review before we get into the new stuff, the real stuff, if you will. We have 5x, we're going to do minus 3y, equals 2, and 3x minus 2y equals negative 1. And what you'll notice about these problems is that we don't have opposites in front of either of them. So then we can start looking for least common multiples. The x's, the least common multiple would be 15. I guess we could do 15 if we really wanted. On the y's, the least common multiple would be 6. 6 is probably a little more manageable. We seem to always be picking on y. We don't have to always pick on y, but it just worked out that way on these examples. So we're going to go for 6. We want one equation to have a coefficient of negative 6, and one equation to have a coefficient of positive 6. So we're going to have to multiply both equations by something this time to get that goal. Let's make the first equation have positive 6. To get positive 6, we have to multiply by negative 2 on both sides. Negative 2 times negative 3 will give us the positive 6. The other equation, shooting for negative 6, we have to multiply by positive 3. When we do that and distribute, we get negative 10x plus 6y equals negative 4, and 9x minus 6y equals negative 3. Now we're ready to add those equations together because we have the opposites in front of the y's. 6y, negative 6y, those are going to subtract out to 0. Again, it doesn't have to be the y's. We could have done the x's and made it positive 15 and negative 15. We would have gotten the same result, but we picked on the y's this time. Negative 10x plus 9y is negative x equals negative 7. Dividing both sides by negative 1 gives us x equals positive 7. And now we have to find y from one of the original equations. It doesn't matter which original equation we go to. 5x, using the first, 5 times 7 minus 3y equals 2. 5 times 7 is 35. Minus 3y equals 2. Subtracting 35 from both sides, negative 3y equals negative 33. Dividing both sides by negative 3, and y equals positive 11. So xy, our solution, is 7, 11. So that's your quick crash course review on solving systems of equations. We can do it graphically, although most of the time we don't go that way. We can do it by substitution, probably the most often used, but we also can use elimination. And this elimination idea actually is going to come up in the future when we start looking at matrices. And a fourth way to solve equations by using matrices. Actually, a fourth and a fifth. There's 2 ways to do it with matrices, but you can wait until Unit B for that excitement. What I want to do, now that we've gone through our big review of systems, is take a look at just a couple applications of systems of equations. And most of these applications are going to come from business and the idea of supply and demand and cost. And we're going to see if we can set up the equations and then solve them by either substitution or elimination. Or graphically, but really graphically is a pain. So substitution and elimination only. The supply curve for a product has been calculated to be y equals 1.5x plus 10. And the demand curve is y equals negative 2.5x plus 34. Now for this, x is the price, and y is the number produced. We want to know what is the equilibrium price and how many will be produced. Now, a little background here about what this is talking about with the supply curve. The supply curve is how much you have stocked in your store. And the problem is when you stock things, there's a cost associated with it. It's taking up space. The demand curve is how much demand there is for your product. So the more your price increases, the more your demand's going to go down. You see that? That's why we have a negative slope here on the demand curve. If you charge a lot of money, they're not going to buy as much. If you charge very little, they're going to buy a lot more. The problem is, if they buy more, you have to have it on hand, and that's going to cost you to be stocked enough to meet the demand. So what you want to find is where those two meet each other, where you have enough in stock to meet the demand, but you're not overcharging, which results in extra stock, or undercharging, which results in you running out of stock. Find that equilibrium price. Well, what you might notice is both these equations are equal to y. If both these equations are equal to y, then they must be equal to each other. In other words, we're going to take this stuff that y equals, and we're going to plug it in for y. The stuff y equals 1.5x plus 10 is equal to the negative 2.5x plus 34. We now have an equation we can solve, moving the variable all to one side by adding 2.5x to both sides. We get 4x plus 10 equals 34. Subtract 10 from both sides. 4x equals 24. And divide both sides by 4. And x, the equilibrium price, is $6. $6 is what we want to charge for our product in order to have the right amount of stock to meet the demand, selling as many as we can. Now we just have to go back and find out how many is that, how many will be produced. And we can go back to our original equation. We can go back to either one. Y, the number produced, is 1.5 times x, which is 6, plus 10. Well, 1.5 times 6 is 9 plus 10, and so we need to produce 19 products. At the price of $6 per item. Let's do one more application, one more that's a little bit more involved in that we're going to have to create the equations. I'm not going to give you the equations on the test. That's too easy. So let's say John sells a product at $5 per item. To produce the items, he has a fixed cost of $12. That's your startup cost, basically. Every time you produce this many items, you have to pay $12 plus a variable cost of $3 per item. So then the supplies for each item on top of the startup cost are $3 per item. We want to know what is the break-even point. At what point does he start making money? Well, one thing we know is his product sells. Let's do a different color here. Let's do gray. We sell at $5 per item. So we might say his profit, or let's call it his revenue. It's how much money he brings in. His revenue is $5 per item. Now he doesn't start with any money, but his slope, his rate of change, is $5 per item. I'm going to use N for the number of things he sells. Now his cost, though, his cost has a fixed cost of $12. That's your starting value. That's your B. And his variable cost, his slope, is $3 per item. So if we take 3M times the number of items plus B plus the starting amount of $12, we've got an equation that represents now his revenue and an equation that represents his cost. We want to know the break-even point. We want to know when both of these are even, or both of these are the same values. So instead of R and C, I'm going to use Y for both of them, because we want them both to be the same. Well, if they're both equal to Y, we can set them both equal to each other. Both of them are equal to Y. So we're going to say 5N, 5N is equal to the other equation, the cost equation, 3N plus 12. In other words, the money that we bring in is the same as the money that goes out. We can solve this really quick by subtracting 3N from both sides. Gives us 2N equals 12. And divide both sides by 2. The number of items he has to sell is 6 items. If he sells 6 items, he will break even on his business. Same amount of money coming in as going out. So that's what we're looking at today, is applications of these systems of equations. There's a few problems which allow you to review graphically substituting and eliminating to solve the systems. And then the real meat, what you're going to see on the test, is these application problems. Can you set up the two equations and solve those two equations about equilibrium prices and break-even points? Bring your questions to class, and we will see you then.